Yeah, I like starting early. When I start with like 2 minutes, when I start at like 1:48 or so, then somebody has a real meaningful question. I'm like, oh, I want to discuss this for a while, and then I end up starting lecture late. And I'd rather start the stream early, and then if somebody has a question, they can ask me, and I have time to answer it. Speaking of questions, anyone figure out Monday's lecture question? I figured it out. I know how to do it. Which one was Monday's? That was trees. That was um, binary search tree to list, if I'm not mistaken. Yeah, so the idea there is to do an in-order traversal. The trick is that you need to collect the results in a list as you go down the recursion and back, more specifically, back up the recursion. So it's pretty tricky, but take a look at any recursion we did where I was returning a list. I had a lot of examples, and I don't know about a lot, but I had some examples of that when we did, for example, oh man, what was it? The permutations, not permutations though, the anagrams. What the hell are they called? Yeah, anagrams, right? When I did the anagrams, the base case returned an empty list, and then as we returned up the recursion, we kept adding. We added to that list, created a new list with more elements, and then returned that. So as you return back up the recursion, you're collecting all the results in the lists and then returning by building bigger and bigger lists each time you return. So that one's a little tricky. I think it's the first time I asked you to do that, where you're really collecting something that's not just an int up the recursion, where you're collecting a data structure. So it's a little tricky, intentionally. Can you use recursion with a tree? Something that you can't cheese because it's way harder to do with a loop than recursion, and collect results in a list. Yeah, I always have the intention of releasing the lecture questions earlier. Today's lecture question was the only one I really went ahead and did that with. It's also one of the few lecture questions that you have what you need to do it by Wednesdays, with Wednesday's lecture, though it is a pretty big leap. So putting your code in repos, I mean, I prefer that it's private and not out there, but I'm not going to stop you if you put your code out there. If you want to put it out there for potential employers to look at, to have a sample of your work. I'm not going to stop you. I should be changing my assignments every year, so that can't hurt things, but, be cautious with it. I'll say, once the solutions are out there, it's, that assignment is compromised. Can I make up Lab 3 next Thursday? I mean, there's a schedule, and the answer is no. Next Thursday is a Learning Objective 4 lab. The last week of class, I keep getting these make-up questions. The last week of class, you can make up all 5 labs, Learning Objective read portions. That make-up week is all 5 labs. There'll be 5 labs. You can do as many as you want. If you're doing all 5, you're taking 10 hours of labs, but you always have that chance. So if you're missing one, you just take the one that you need. And if you're close at the end of the semester, if you're close in learning objectives, I don't intend to just fail you, like, oh, you didn't get all 5 learning objectives, you fail. If you're close, I'm going to work with you and try to get you to learn the content that you're missing and try to get you over the line so you can pass. So a lot of you are really nervous that you're very close, but you're missing 1 or 2 things and you're worried you're going to fail. I'm going to work with you. Focus on learning what you're misunderstanding, and then I'll give you the opportunities that you need. Within reason, I mean, eventually final grades are due and I got to submit. But I'll work with you past the last week of classes, if that's what it takes. Made you switch from Java to Scala? That'll be a longer answer. I'll still end up starting late. The short answer is Scala has better support for concurrency and functional programming. Those are 2 topics we want to talk about. Yeah, the TA say you shouldn't post your code, but my official stance is that I'm not going to stop you. I'm not going to be thrilled about it either, but at the end of the day, my job is to help you get a job, and that's something that can help you get a job. In good conscience, I can't say no, but I don't like to see it. I don't like that solutions are out there. What's up, JS? What? Graph lecture question, it says, see if two nodes are connected, but isn't there a method that does that already named connected in the example? No. I don't think so anyway. I mean, if there is, then you got the lecture question done, but I don't think I leaked that solution. Oh. I know, right, P? You believe this is the end of LO4? This semester seemed to just fly by. Most semesters do, but I feel like this one even more so. I think because it didn't feel real. It was just kind of an illusion of a semester, since we're not meeting on campus. Alright. Pathfinding with BFS. Let's do it. Yeah, the semester feels accelerated. I don't know. Yeah, do it small. I kind of did give I didn't give the code away. I mean, and this, to an extent, this is how things should work. In lecture, I tell you how to do the lecture question, and then the lecture question, you actually produce the code that does it. But I would argue that in most cases, I mean, there are a lot of lecture questions where I expect you to take what you learned in lecture and take it to the next level. For example, when I talk about testing, I throw a factoring question at you. I do expect you to be able to take that to the next level and test the factoring, mostly because to find the prime factorization of an integer, I think, is a 115 level question, and what you're really studying there is how to do it in Scala. So there are things like that, but in most cases, in lecture, I say, this is how you do the lecture question, and then you just do the lecture question after. But if you're behind on something else, then it's going to feel difficult. And some of them are just flat out difficult. Factoring with functional programming, that's pretty tricky. I showed you how to do recursion and functional programming, but that thing, it does take it to the next level. So let's talk about pathfinding with BFS. Let's do this. Are we really at 37 viewers? Oh my goodness. And then the rest of the class, all but 37, are going to say, why am I doing so bad? I'm so far behind. I have one guess of why you're doing that bad. I hope that number's off. That can't be that low. 49? Okay. Still, that's pretty bad, though. But my hope is that a lot of y'all are watching this on YouTube. Yo, what's up, YouTube? But I don't know. Things like that just push me towards mandatory attendance, which I don't want to do, and most students don't want me to do. But I mean, if you're not going to show up. Pathfinding with BFS. So today's lecture question, very similar to Wednesday's lecture question, actually, but instead of just finding if two nodes are connected in a graph, we want to find their distance to each other, where distance to each other is the length of the shortest path between them, which I have a few slides. I'll talk about that. And then test to make sure that this is working. And you can assume that the two input nodes are connected. So we're not going to have, if I were to add more to this question, I would say if they're not connected, return -1 for the distance. We're not going to do that. We're going to skip that and just say, assume they're connected. And in all of your testing, any test that you write, make sure that the two input nodes that you are testing with are actually connected. So that's the lecture question. So there are a few definitions that we have to get out there to be able to complete this lecture question. A path, we seen last time. A path is a sequence of nodes that are all connected. All adjacent nodes are connected by an edge. So we've seen this. This is a path. Start at Lincoln, which for some reason my N got cut off there. Lincoln, MIT, Utah, SDC, Rand, UCSB, SRI. That's a path in this graph. And the length of a path, which is the new definition we're talking about, the length of the path is the number of edges contained in that path, or the number of nodes minus 1. So this is a path of length 1, 2, 3, 4, 5, 6. It's a path of length 6. The next definition, distance, which you have to compute for your lecture question, is the length of the shortest path between any two nodes. So Lincoln and SRI, we just saw a path of length 6 to connect the two, but there does exist a path of length 3. 1, 2, 3. There is a path of length 3 that connects them, and there's no paths of length 2 or 1. There's no path shorter than 3. So the distance between Lincoln and SRI is 3. Even though there exist longer paths, we're only concerned about the shortest one. The shortest one is 3. Distance between Lincoln and SRI is 3. Distance between something like RAND and BBN, well, they're connected by an edge, so we can just get there directly in one step. That's a distance of 1 because there exists a path of length 1 from BBN to RAND. And technically, I don't think I test you on this at all in this class. It's not something we really have to worry about. But like the distance between BBN and itself would be 0. You can get there with a path of length 0. You're already there. The whole path is just that node. So what we want to do in today's lecture and in the homework assignment and in today's lecture question is use BFS to find the distance between two nodes, and then we can actually extract the path between those two nodes, which we had to do for the homework assignment to be able to find that that shortest path that should be taken. So there's a natural progression between Wednesday's lecture question, today's lecture question, and the homework. We're using BFS for all three of them, but we're just getting more and more information each time. First, we just want to know, are these two nodes connected? Now we want to know what's the distance between the two. And for the homework, what's the actual path? What's one of the optimal paths that has that distance, that shortest path length? So let's run BFS again. Well, we briefly went through BFS on Wednesday. Let's go through it again. We'll go through it like 3 times, I think, today. We're going to go through BFS again and talk a bit more about the details of what's going on. So instead of just computing the connected component like we did on Wednesday, let's track all these paths and remember how we got to each node. So let's run the same start as we did before. Let's start at UC. Oops. Let's start at Carnegie. Let's start at Carnegie this time. And we're going to keep track of the nodes that we're visiting in a more detailed way. So let's put Carnegie up here. I'm going to add them in a specific structure, and I'll talk about the structure afterwards. But let's visit Carnegie, visit all of its neighbors, Case and Harvard, and kind of draw the edges always going down in this new structure that we're writing. Explore the neighbors of the neighbors, Lincoln and BBN, and then for each one of these, explore their neighbors. And at this point, it's arbitrary how we visit MIT, where we visit MIT from. It's whatever one we end up adding first between Lincoln and BBN. It's just up to our implementation how it decides, how it processes these. We're going to say that Lincoln got there first. Once Lincoln added that edge, then when we visited BBN, we're going to see that MIT was already visited, and we're not traveling this edge from BBN. We're only going to visit RAND. So this edge is never traveled because MIT was already visited by the time we explored BBN. And same thing, we're going to keep going. MIT is going to explore Utah. RAND is going to explore 3 different nodes. And then for each one of these, whatever order we end up visiting them in, SRI can be discovered by any 3 of these nodes. I think I gave it to Utah, and then Stanford is going to be explored through UCLA. That's the only way we can reach Stanford in that on that iteration. So each time we just explored new nodes and built this structure going down visually. So we built this structure by navigating the algorithm, the BFS algorithm, in this way. And guess what? This is a tree. We turned our graph into a tree, and we could call this a BFS tree. It's the tree generated by running BFS. There are no cycles in here because every time we were about to add a cycle into the structure, we noticed that the node we were about to add has already been visited, so we didn't visit it enough. And you're right, Andrew, there's levels to this. It has levels. So if we picture this visually, where each kind of round that we went through the algorithm, we discovered a new level of nodes. And we can label these levels. We start at level 0, 1, 2, 3, 4, 5. And here comes the magic. Each level number is equal to the distance from the starting node for the nodes on that level. So level 0, Carnegie, distance 0 from itself. The next level, Case and Harvard, these are the nodes that are connected to Carnegie through one edge. Level 2, these are the nodes that we can reach from Carnegie with 2 edges, because we explored all the nodes that are connected to Carnegie and then all the nodes that are connected to those nodes. These are the nodes we can reach through 2 edges, then 3 edges, 4 edges, 5 edges. Stanford and SRI, we can stare at this graph for a while. We're never going to find a path from Carnegie to Stanford or SRI that's shorter than length 5. There's no way to get there. We could, maybe we made different choices in these edges. 1, 2, 3, 4, 5. It's still going to be 5. 1, 2, 3, 4, 4, 5. Still going to be 5. We can't get there any faster. 1, 2, 3, 4, 5 to Stanford. We can't find a quicker path to get there. That doesn't exist. If it existed, breadth first search would have found it. So that's my claim, that the level number here, the number of jumps that we took with BFS, is the distance, because BFS is always finding the shortest path from the start node to every other node in the graph, or at least the connected component of that graph. Which is all great, and visually this looks fine, but how the hell do we code that? This is a tougher thing to code. So visually, okay, I can draw this tree as I'm doing breadth first search. So if I gave you this is a lab question and you had pencil and paper, you could draw out the tree. You could run your breadth first search and generate this tree. But how do we do that in code? How do we track these levels in the code to be able to run this algorithm and then say, okay, what was the distance to this node? Which is, exactly the lecture question. That's what we want to be able to do. The question we're all wondering, exactly. It's almost like I knew you'd be wondering that. So let's talk about how to do this in code. So for that, we're going to need an extra data structure. I'm going to use a map of strings to ints or ints to ints. I would do this with the indices in the code, or the IDs, not the node names. So it would be int to int, and I'm going to track the distance from the start node to each one of these nodes. So we initialize this. Carnegie is going to be distance 0. And then each time we visit a node, we're going to take the value, the distance of the node that we're currently exploring, add 1 to it, and then add those values to the map as we're moving through this list. So we initialized, exploring Carnegie. Orange means it's explored already. Add it to the queue. And then this is the first node that we visit. We're going to visit Carnegie, explore all of its neighbors that haven't been explored, mark them as explored, and add them to the queue. And as we explore them, add 1 to the distance of the node from which it was explored. We're going to look at Case, explore Lincoln, mark it explored, add it to the queue, update our distance table. Since we're exploring this from Case, we're going to say, Case, what's your distance? It's 1. So Lincoln's distance is going to be the distance of wherever it was explored from, plus 1 to add this new edge that we're traversing. So Lincoln, distance 2. Harvard, DQ that. Explore BBN, add it to the queue. BBN, what's your distance? Well, I was explored through Harvard. Harvard, what's your distance? 1. Add 1 to that to add this new edge. And these distances, they're all distances from Carnegie. We started at this node, so we're going to find the distance from Carnegie to any node in this graph. So we just keep exploring nodes and adding 1 to the distance as we're traversing. Go back to our queue, Lincoln, explore MIT, mark it explored, add it to the queue. In MIT, what's your distance going to be? Well, I was explored from Lincoln. Lincoln's distance is 2. I don't know how we got to 2. I don't care. All I know is that Lincoln, if your distance is 2, I'm going to add 1 to that because you got to me through 1 edge. My distance is going to be 3. And just keep repeating. BBN, we're going to explore all the unexplored neighbors. MIT is already marked explored, so we're skipping that one. And the other neighbor, Rand, is not explored, so we're going to explore that with a distance of 3. BBN's 2 plus 1. Visit MIT. Explore Utah. Utah's distance is going to be 4 because MIT's was 3. We added 1 to it. Rand, we're going to make 3 explorations, explore 3 new nodes. They're all going to have distance 4 because they were explored through Rand, and Rand has distance 3. We're going to explore Utah. DQ Utah. Visit all of its unexplored neighbors, which is SRI. And here's where we have to have those checks where we're saying if a neighbor is already explored, don't explore it. Because, well, especially with MIT as well. But SDC was already explored through Rand. And SDC had a distance of 4, taking that path through Rand. 1, 2, 3, 4. So Rand got there first by the nature of this algorithm. If we waited for Utah to discover it, well, Utah has a distance of 4. So SDC would end up having a distance of 5 like SRI does. But it doesn't because the algorithm is going to guarantee that that shorter path is going to be found first. Since we're ordering everything in the queue is actually going to end up being ordered by distance. So it's going to find SDC through that shortest path before it finds this path. And that's a guarantee from the algorithm. We can just take that at face value in this class. In 331, you'll explore exactly why and prove it mathematically. So look forward to that. I think it's fun. Most students don't. But hopefully you find that fun. And the algorithm is going to guarantee that. We can just take that as a fact in this class. Then UCLA, it's going to explore Stanford. UCLA is 4. Stanford is going to be 5 then. Add 1 to it. And then the rest of the nodes, each time we DQ one of these, we're going to look at all the neighbors. They're all already explored, so there's nothing to do, nothing to do, nothing to do, nothing to do. And then we reach the end of the algorithm, and we have a map mapping each node to its distance from the starting node. Yeah, Ellipso, you all right there? I'm concerned now. So each time you explore a node, you're going to update this table with a value that's 1 plus the value of the node that explored it. So each time we find a new node that hasn't already been explored, whatever the distance is from the node that explored it, just add 1 to it. And you can keep track of all these distances without recomputing. Like, we're never looking all the way back to Carnegie. We're just adding 1 each time and remembering those values. And each time we explore a node, we know that at the time we're exploring it, that is a shortest path that we found at the time that it's explored. I'll let that settle for a second. Okay. Everyone good on distances? This sounds so simple. I like to hear that. I like that. Usually hear the opposite, so that's a good change of pace. Hopefully the rest of the class agrees with you. Why is Harvard and Case below Carnegie in the list? Because this is a map. So our maps, any key value store doesn't have, I shouldn't say any, but the ones that we use don't have a particular ordering. So I just listed all the nodes in whatever order. And then the values that they map to is what's important. But the order here, the order of the nodes has no meaning in this example. It's just I initialized the list. So when we start, I don't have any information, and I just initialized every node to infinity distance, and then I started filling it in as I went. So before I run BFS, I don't know what the distances are going to be with all these nodes. So they can just be in any order. And I think the order was just as I saw them. Like I read all the nodes. This is the real answer of why. Is I read all the nodes and I started at the top and went left to right. So UCLA, Stanford, SRI, Utah, SDC, MIT, BBN, Lincoln, Carnegie, Harvard, Case. That's the order that I have them in. But it's completely meaningless. It doesn't really mean anything. It's just when I was typing this, I would look over at the graph and be like, okay, UCLA and then Stanford. So don't take any meaning of that. That's an arbitrary order, and that's how I chose the arbitrary order. Which is accurate for maps in the code because the order doesn't matter. The order of the keys is meaningless. There is no order to those. What they map to is what's important. Okay. So that gets you through the lecture question today. In my BFS, you noticed from Wednesday's lecture question, but my BFS in the code does do some of these computations. It leaves a little bit for you to still do, of course, because I don't want to give away everything. Today's lecture question answer, that's already out there. I just did that. You missed it, P. You can already do today's lecture question with what I just showed. So the rest of what I want to talk about is how to do the homework. So that's great to find the distances, but that's not what the maze homework is asking you to do. I'm not just saying, here, you find the distance from the start to the end. That's not what I'm asking. I'm asking you to actually find the shortest path and actually compute that path and traverse that path. That's what we actually want to do. That's where it really gets useful to be able to do that. So we have to change this a bit. We have to modify our algorithm a bit to be able to do this. And this is what I mixed up my variable name in the code. I should have updated this in the repo. But I have that distances map. That distances map is actually doing the pathfinding that we'll see that I'm about to show here. So if you're wondering why that's set up weird, but hey, I have to leave something for you to do for the lecture question. And the homework, believe me, there's plenty enough to do. Just adapting the breadth first search code and algorithm to a specific application of actually solving this maze that I'm faced with. There's still a lot to do there. You already finished the homework and expansion? Dang. Alright, so this isn't going to work, just storing the distances. So what we're going to do instead... Just kidding. Oh, got him. What we're going to do instead is not remember the distance, only the distance, or the distance at all. We're not going to track the distance at all. But we're going to remember the node that discovered each node. So I'm going to have some way of marking, and I believe I use -1 in the code, but some way of marking the start node. And then each time I explore a node, I'm going to mark where I found that node from. Where did I come from to find this node? So I start at Carnegie, I explore Case and Harvard. Case and Harvard are going to remember that they were explored from Carnegie. Lincoln is going to remember that it was explored from Case. BBN is going to remember that it was explored from Harvard. MIT is going to remember that it was explored from Lincoln. Rand is going to remember that it was explored through BBN. And hopefully you get the idea of this part of it. each node is going to remember where it was explored from. And that's the only information we're going to store for each node. And P is got it in chat. What we're going to do now, how is this information useful for pathfinding? Well, we're going to backtrack. So say we want to find the path, the shortest path, or a shortest path. There can be ties, and in the homework, there will be a lot of ties in the distance for any given input, any given start and end point. There can be many different paths. For some of the testing, I give you just an open level with no walls in it and ask you to go diagonally. Well, you can go, if I need to go up and left, I can go left, then up, then left. I can kind of zigzag throughout. There are tons of different paths you can take. But we want to find a shortest path. And each time we make an arbitrary decision, like does MIT, is that explored through Lincoln or BBN? There was a decision, it didn't matter, but we ended up finding this shortest path instead of this shortest path. So there are arbitrary decisions that can just be broken however you want, at least for 116 purposes. So how does this information help us? We want to find a shortest path from Carnegie to Stanford. What we're going to do is start at Stanford and backtrack. We're going to say, Stanford, who discovered you? Where did you come from? And we're going to look it up and we're going to see, whoa, UCLA is the node that found Stanford. So we go to UCLA and we start building our path backwards. Ending at Stanford, Stanford was found from UCLA. So we ask our map, hey, UCLA, if I can, oh, it's highlighted. Hey, UCLA, who found you? Where did you come from? Well, I came from Rand. Rand, where did you come from? Well, I came from BBN. BBN, where did you come from? I came from Harvard. Harvard, where did you come from? I came from Carnegie. And Carnegie, where did you come from? I came out of thin air. I am the start of the node. You've reached your destination or your starting point since we're going backwards. And Carnegie says, we're done. I'm the last node or the first node. And then you have your path. So you're going to start at your destination and work your way backwards until you get to the starting point. And now we have a path. We have a path from Carnegie to Stanford, and it is a shortest path. It does reflect the distance of 5. And we could, and at this point, we can also compute the distance. So we can also do distance using this pathfinding just by getting the path and then asking it for its length. Hey, path, what's your length? That's the distance between these two nodes. Any questions on that? Jesse's path to university. Yeah, going to every college. Reminder that this is this is internet pathing that we're doing. These are all nodes in the early days of the internet. These are all servers in the early days of the internet. So if someone at Carnegie needs to send an email to someone at Stanford, if all the routers are optimal, if the pathing is optimal, this is the path that it would end up sending, assuming all connections are equal, which isn't true. So, but that's one assumption that we have. And by the way, just for anyone wanting to think ahead and look ahead a bit, the pathfinding that we're doing only works for what we call non-weighted edges. Once you have edge weights, this doesn't work at all. For that, we would need something like Dijkstra's algorithm or A star to be able to find shortest paths if we have weighted edges. So like if this edge is a lot shorter than this edge, like not just visually here, but it takes a lot longer to send a packet from BBN to Rand than it does from Carnegie to Harvard. If that's the case, then we can't use BFS for pathfinding. We can only use BFS for pathfinding because all of our edges, we're assuming, have equal weight. So just a heads up for future stuff. Dijkstra's, don't you worry, it's coming in 331. You'll learn about that as well. Was the distance map do by default in the given BFS? The distance map does this by default, the pathfinding. It remembers the previous node. But I leave some, the computation and stuff up to you, because I'm not just going to do your homework for you. But BFS is tough enough that I wanted to give you an example implementation. Yep, and you need to translate this into code. So when you reach the end, so you run BFS, you generate this table, and then you want to find the path. You use this table with a loop. You say, well, the value at the node that I'm currently at isn't start. Keep iterating, keep finding the next node, and then looking up that node, and each time building your path in some data structure, probably a list, as it's shown visually here. And then once you read start, that's when your while loop is done, and then you have your path, and then you can do all your path goodness after that, depending on what you're doing with the path, if you're just returning that or finding its distance or whatever you're doing with it. Yep, it's a list of individual previous node references. That's a good way of putting it. It's like a tree. It's like this tree, except each node remembers its parent only, has a reference to its parent. So Stanford has a reference to UCLA, has a reference to Rand, has a reference to BBN, has a reference to Harvard, has a reference to Carnegie. So we're starting at any node and then going up this tree until we reach that node. So each time we explore a node, we're remembering where we came from in the previous level, is what we're doing there. So Stanford, UCLA, Rand, BBN, Harvard, Carnegie should be the exact same thing that we did right here. Stanford, UCLA, Rand, BBN, Harvard, Carnegie should be the exact same thing. I don't have good enough short-term memory to remember, but it certainly should be, or else I did something terribly wrong. Yeah, this homework should be easier than the last one, partly because I give you so much BFS sample code, and partly because these 2 lecture questions are so heavily related and strongly lead into the homework. That the homework, there's enough left to do, but not so much compared to the previous homeworks. The estimate might even be able to be lower than 15 hours. Don't miss this one. If you're keeping up with class, make sure you get this homework. It could be a very difficult homework, but I give you enough structure, enough scaffolding that, I don't know, I kind of nerfed it, to be honest. That said, it's still, there's still work to be done. It's not easy, objectively easy. Just a bit easier, in my opinion, than, say, genetic algorithm or calculator or microwave. It's probably more on the level of, I don't know, maybe a little harder than the homework ones, especially rhyming dictionary. It's definitely harder than that, though. All right, everyone good on pathfinding and tracking the path? So for those of you who haven't ran the GUI yet, yep, and a yee, all right. So for anyone who hasn't ran the GUI yet, this is the GUI that I give you for testing. For the maze solver homework, you'll spin it up. You have a character here and the end of a maze here. And when you click on a green square, your character should move to that green square. Simple enough. From the user perspective anyway, it's like any MMO or any, I shouldn't say any MMO, but any game where you are moving by clicking. You click somewhere on the screen and then your character moves there. And if there's something in their way, they'll walk around that obstacle. So that's the idea that we're building here. It's more of a proof of concept that we can build an MMO with the things that you're learning in this class. We can do all the stuff. We can get that all working. This is networked. You are going to run a server and then open it in your browser. So if you had this running on physical server connected to the internet and had 2 people open it in their browsers, guess what? You got a multiplayer game. And then you add combat or whatever game mechanics you want to it. You got a freaking game. But this is the idea. You click somewhere on here. So if you're here at the start, you click on the exit. This character should find the shortest path, which is this path right here. So your character needs to travel that path. It shouldn't get caught up in some things like heading straight for the goal and getting stuck right here. It shouldn't go through all these whoop-de-doos here. This is way long. That's a long path. It needs to find that shortest path and not get stuck in any of these dead ends. Might sound like a daunting task at first, but once we're running BFS does a lot of the heavy lifting for us. We're not gonna have to code this and say don't go down the dead ends and stuff. We're just gonna say run BFS, and once you find the goal, backtrack, and that backtracking is gonna take you down this path because none of these dead ends are gonna reach this goal. But how does this help us with this? This isn't a graph. How am I supposed to do this? You're going to get this as a 2D array. You're going to get this as a list of lists of tiles, all with XY values. This isn't a graph, and BFS works on graphs. So this is where the bulk of the difficulty of the homework, since I gave you so much BFS code, this is where the bulk of what you need to do is converting this grid into a graph. So if we think of each tile in the grid as a node in a graph where two adjacent nodes that are both on the path that neither of them are walls, they're going to be connected by an edge. And just a side note, the numbering for this graph starts up in the upper left corner. I don't think this came up in this semester yet. It's the upper left corner is 0, 0, and then positive X goes this way and positive Y goes down. So in any images or screens or videos, this is the convention that the upper left corner is always 0, 0. So on the monitor you're looking at right now, the upper left corner is pixel 0, 0, and then Y, positive Y, is in the down direction. So it is a little reverse from what we think, but that's consistent across all multimedia, images, videos, monitors, websites. The upper left corner is 0, 0. So just keep that in mind when you're coding, that this is 0, 0. Let me be careful here. 1, 0, right? Okay, I'm embarrassed I had to think about that so much. 1, 0, 2, 0, 3, 0, 3, 1, 3, 2, 3, 3, 4, 3, etc. All the way through the graph. So we have this grid system, and we convert that to a graph by giving a node. There are several ways you could do this, by the way. Either give nodes to every single tile, and then connect the nodes that are adjacent and both on the path, or only create nodes if the node is on the path. So if you read a tile and it's impassable, which has each tile has a Boolean, whether it's passable or impassable. If it's impassable, that means it's a wall. You can't move through it. That can't have edges connected to any of its neighbors, so you could just not add a node there at all. Would also work. But any two adjacent nodes, and notice that we can't move diagonally. No diagonal nodes, but any two adjacent nodes in the up, left, right, down directions that are both on the path, that are both passable, there needs to be an edge connecting them. And by the way, if you're wondering, this slide is probably the most work I've put into a slide, just because I painstakingly made each one of these nodes and edges by hand. I have no regrets, but you know, I wish I had a better way of doing that. I wish I used a better way. I should have wrote a program to do it. So now that we have a graph, what we see when we play this game, and I use the word game pretty liberally there, when we run this in our browser, we see this. The computer sees this. So the computer just sees the graph, and now guess what? We can run breadth first search on this graph, and the computer can work with that really well. But we only see this. This is the part that we see is the actual tiles. The computer is going to see the graphs. The graph representing those tiles. Yeah, I should have used Paint. Why didn't I use Paint? So I did it in Keynote, just because that's what my slides are in. I should have just done it in an actual graphics program. Keynote did not like having this many elements on screen. Every time I would cut and paste the rows, and I'd have to sit there for, I don't know, felt like an hour, but it was probably like 20 seconds, just waiting for Keynote to process that all those new objects were added. It would have been a lot faster in a Paint program. Which brings us to our lecture question. Are we actually ending early too? Holy moly. I felt like I didn't rip through those slides either. I think that was just a good pace. I think I get confused when I see 46 slides. I'm like, oh, I have a lot of slides. But a lot of those are just single clicks as I'm running through an algorithm. Those are very quick slides. So I probably didn't add more because I didn't want too much stuff. 10 minutes early. I don't know if this has ever happened. Let's, I mean, we can do more things. We can always do more things. I think I usually do go through the code actually in this one. So here's the breadth first search code that I give you. And for your lecture questions and your homework, you can use this code, but be careful about how you're using it. You're not just taking this algorithm. It's set up so you can't just paste this algorithm, this whole method, I should say, in your code. It's not going to work for you because I made sure this returns unit. It doesn't give you any useful information. It just runs the algorithm. What you want to do instead is grab this code, copy, and this is the one time where I'll tell you just copy and paste. Maybe I should make you code this up. Maybe some semester I will. But at this point in the semester, you're also broken down already. I want to give you something. So copy this, go into your lecture question code, paste it, and then start modifying this to do what you need it to do. So this is going to track the where did I come from information in this map. The start ID, I'm going to use -1 to mark that this is the start. And then I'm going to be careful about the way I build my graph to make sure I don't have a node with an ID of -1, or else, of course, everything's going to break at that point. So I mark my start ID as -1. And then each time I explore a new node, I'm going to update this map to say this node was found from the node that I'm currently exploring. So I got I went to my adjacency list, got the neighbors of the node that I'm currently exploring, and I'm going to iterate over all its neighbors. As long as that neighbor was not already explored, I'm going to add it to the queue. I'm going to mark it as explored, and I'm going to update its distance, kind of. I named this distance because it used to store the distance when I wrote it. I didn't change the name. But it's going to remember the node from which it came. So this node was explored through this node, and then that's going to help me do my backtracking. And then for your homework, you still have to do the backtracking and generate the path. It shouldn't be too difficult, I don't think, given all this code. But you want to start with this. You're never calling my BFS, but like in your lecture question, this is where you start. Oops, I should hit enter. I should hit the other button. For distance, this is where you start. Then you can start at this thing, or just change this. What I usually recommend, just change this to start ID. And then you're expected to understand enough of this code to be able to modify it to fit your specific needs. So I'm doing the breadth first search algorithm in general for you, and by coding it up the way we saw it in lecture, but you have to understand it enough to know what you need to change, which is why there's still enough challenge in these lecture questions to be worth doing. Oh, that was the question in chat. Connected, that's just saying if they're connected by an edge, not asking whether they're connected in the graph. This is connected by edge. So this would be, do these two nodes have distance 1, is what this thing's asking, which doesn't help you for your lecture question, for Wednesday's lecture question. Is path, this used to be a lecture question. Just given a path, tell me if this is a valid path or not. That's something you'll have to do in your homework to write your testing. So when you're testing, you're going to ask the Pathfinder, hey, give me a path, and it's going to return a path. You have to check a few things. Make sure it's a valid path. It only contains nodes that are connected to each other. It also has to not contain any impassable tiles, And then third, it has to have minimum length. Its length has to be equal to the distance between those nodes. It could be any one of the valid shortest paths, but you have to make sure that it's valid and has that shortest distance. Its length is equal to the distance. So yeah, this used to be a lecture question, and then I don't know why, but I decided it shouldn't be a lecture question anymore, so I just give you the solution and then give you new lecture questions that are all related to BFS. Yeah, if you didn't see these yet, this is where you write your 2 lecture questions for Wednesday and today. Could you recap, summarize pathfinding with nodes and backtracking? I mean, that's what we did all day. You can watch the VOD and look it up. I'll summarize it, but recapping, you're remembering. So you're remembering where each node was explored from. So with pathfinding, we're going to remember each time we explore a node when we're running breadth first search, we're going to remember which node we explored it from. So when we explored Harvard, we remembered that we explored it from Carnegie. When we explored BBN, we remembered that we explored it from Harvard, etc. And then when we want to find a path, we're going to look at this map of all of the where did we come from nodes. If we want to start at something like Stanford, we're going to just keep looking through this. Stanford came from UCLA. UCLA came from Rand. Rand came from BBN. BBN came from Harvard. Harvard came from Carnegie. Carnegie was the start. So we can build the path with this information. Yeah, OBS crash. What the hell? What the hell's up with that? Which means I lost chat too. So if you had a question from before that, make sure you repost it, because I lost all my chat history. I had to restart OBS. And that's where I read my chat from. Yeah, rip chat. And then y'all had to refresh too, probably, which means we all lost chat. I hope that's not going to be a regular thing. OBS did... You know what? I know what it was. This is why I learned my lesson so many times. I still haven't fully learned it. OBS kept telling me there was an update, and I said, no, I'm not updating. I never update anything mid-semester if everything's going right. And finally, the other day, I'm like, you know what? Whatever, I'm going to update OBS. And now it crashes. Yay, thanks for the update, OBS. Fan-friggin-tastic. Could you please review the last portion of Makeup Lab, just the syntax and how the tail recursion portion was done? So you don't have to worry about the fact that it was tail recursion. You can ignore the fact that it's tail recursion, as long as you're explaining the recursion as it goes. But the question just had the tail recursion annotation on it. Now, that doesn't change any of the functionality. The syntax, if it was concatenating lists, like the double colon, was merging lists together and values together. Yeah, I said a lot. You don't have to worry about the tail recursion. That's not an expectation of the course to understand tail recursion itself. It's just something I like talking about because, you know, it's related to the stuff we're talking about. Did you show a running example? There was no... I might have been thinking of the other one. I thought there was a video for this. Do we not have a video for maze solver? I don't know. Can I show... Let me think of the closest place I have the code. Slice and plus plus. And if it's a syntax issue, if you gave enough detail to show that you understand the question, and you just didn't understand slice and plus plus, that's something we can overlook. Like, we can give you credit for that. But slice, that's the same as substring, and plus plus is merging the lists. Maybe I can. I mean, I can do it a really cheesy way and hold up my laptop. Do I want to do it like that? I might just do it that way. This is going to be horrible. Get ready, but yeah, let me do it from my laptop and hold it up. Actually, no, I don't have to do it like that. We want Togo. Network preferences. Yeah, we can do this. We can do this. Right? No, that's going to take too long to set up. I'm just going to hold up my laptop. If I had more time to set it up, I would, but... Let's do it. High tech here. So I have a different map set up. I added this big open area because a lot of students last semester had issues with wide open areas, so I made that just to show them how wrong their code was. But if I click somewhere, my character is going to move to that place. And oh my goodness, this is hard to do. And if I click like down here, it's going to take the shortest path to that location. So you click, and the circle moves to where you clicked without moving through any walls and takes the shortest path. Mac reveal. Look at that, the circle moves. Whoa. It's high quality stream right there, holding up the laptop. So I was gonna, let's see if I can do that quickly. Problem is I don't have the code downloaded on this at all. Let's see if I can quickly do this. It is really satisfying to finish. You damn right, Marcos. It's even when I did my solutions, when I finished it and saw the thing move, feels good. Feels good, man. I would argue that most of the assignments in this course feel good, but you know I'm biased because I made them. But I think they do feel good. When you do physics engine and the game works, oh my god, that feels so good. Even making my solutions, I'm like, it's a freaking game. Like, look at this thing. Oh, it already exists. All right, file, open recent, maze solver. I need to resize. Pathfinding, these are the two methods that you write. And let's try this. Nine two 168. I should know those off the top of my head. It's embarrassing I still don't. And let's run this. Not found. Not found. If you get that not found error, by the way, I don't remember what screen it was on if you saw it, but I was opening it in IntelliJ and it kept saying not found. If you do see that, open the file from your File Explorer or Finder, whatever it's called on your machine, and open the file without using IntelliJ. And it should work for you. But I'm not going to get the connection. 158080. It's like I'm not going to... I might not get there on this one. It happens sometimes. If that's not going to connect, I don't really know. I don't really have a good plan to fix that. Right. Let me double check the IP. Let me double check my network. Yeah, I know it's connected. Goodness, Windows. It's not. What do I need to see? Yeah, whatever. Yeah, we're not going to get there on that one. I was trying to connect the networking through my computers. I thought this should work, but if that doesn't work, I don't have a second guess. The physics engine was held together with duct tape. Yeah, a lot of code is. Yeah, especially when you're a freshman, like you're not yeah. That's what a lot of your code's going to look like. Sometimes I forget that when I'll have a solution, especially for lecture questions. I have my solution in mind, like I take the lecture content and you apply that to the lecture question, and I have like 5 lines of really elegant, clean code. And then I'll be helping someone in office hours, and they have like 50 lines of just conditionals and loops and everything moving all over the place. I'm like, oh my goodness, maybe this was a little more than I thought it was going to be. When you don't understand how to take the concepts and translate it to code, which you shouldn't yet because you're just learning it. Like my genetic algorithm is. Let me make sure I pull it up so I don't mislead anyone. Genetic algorithm solution. No, it's a little deceiving though. Right, because I created an animal class. That animal class is 40 lines of code, which handles the mutations in mating and everything. Then my genetic algorithm itself is 50 lines of code. So under 100 lines of code for genetic algorithm to be efficient enough to be used in the towers game, where the towers are shooting. That's using my genetic algorithm. But then when I see code from people who are first learning this stuff, it's not going to be under 100 lines. Some of yours is, mostly because some of you found out that you didn't have to do all of the things that I said you should do. Like my recommended algorithm, that's really efficient and nice. But to get credit in Autolab, which is fairly lenient for this one, you don't have to be crazy accurate and precise. But some of you found out that you could skip like mutations. I think one student even skipped mutations and crossover and just did pure random guess and check. And it was enough for my grader. My grader was pretty generous. Which, given that, because now that I know somebody got away with that, I might tighten that down next time and force you to be more accurate. It's a server and website. And that's why that week 2 lab exists. Because if you were having IntelliJ problems right now because your versions were off and you got through the first part of the semester, then you get to these homeworks and I'm like, hey, it's another server in GUI, and you're like, my IntelliJ won't run that. This is where those issues would creep up and where they did creep up before we had that week 2 lab. I made sure week 2, can you run a web server and a web page and have them connected? Because we're going to be doing that a lot. It's going to be important for these homeworks. Because I use that a good amount. Yeah, no kidding, do it small. I won't rant too long, but yeah, so much of the class doesn't show up to lecture, and also Piazza gets blown up every day. Like, show up to lecture and you won't need so many Piazza questions. And maybe they're watching the videos, but I don't think so. I think most of the video views are people who watched the lecture live, re-watching it. The class is really bimodal. It's students who are trying and students who are not trying. And I don't know what to do about it. It's just so exacerbated with online only. I've never seen the problem this bad. Mango Mutiny, have fun at work. If during the interview my code breaks a little, do I fail the interview? It depends on what broke. And in a lot of cases, not. When I review those, when I do my verification, if you got poor interview scores because of the demo, but your code, you got a full credit in Autolab, you got the primary objective complete in Autolab, and your explanations were really good. So if you're able to explain all your code and your design and approach and everything, I'm usually giving you credit even though your code broke during the demo. Because I can take that, maybe something just went wrong during the demo, but you clearly got everything else. If your explanations are weak and your code breaks, but for some reason you have full credit in Autolab, well, I'm a little less forgiving in those cases. But if that's the only thing that went wrong is it breaks a little during the demo and everything else is flying colors, you're getting it. I'm going to give it to you. Yeah, well, that's what I'm thinking. It might be a firewall issue. It's just not something I'm going to debug live right now. I just don't feel like going through all that. But I feel like I've done things like that. It also might be because my desktop is wired and my laptop's wireless, but I don't think that should matter. I think it should share the same IP pool, and my router should be able to resolve that DNS. But I don't know. It's just not something I want to think about right now. I was hoping it'd work. I tried once. I'm not going to keep trying. Unless it was just a silly issue and I can just refresh. I haven't even tried to refresh yet. Nope. It's open too much. I don't know. It does say connection refused though, but on my laptop it's not giving me any logs that there was a connection attempt. Are you using PyCharm? Oh, it's IntelliJ. It's very similar to PyCharm. It's made by the same company. Yeah, less than 100. Yeah. Well, and with functional programming, it really cuts down the lines of code. Each line is really complex. Can be complex, but each line is doing a lot of work. But it compacts your code so much. So there's a lot I could still compact. Like all my mutations, that's done in one line. Granted, actually that's built in that's in my other class, my animal class though. So that's more than one line. Are you asking me about PyCharm? PyCharm and PyTorch and TensorFlow for Scala. I don't use PyTorch or TensorFlow for Scala. Unless you're asking someone else. Maybe I just missed something there. Janelle, go interview. Good luck, Marcos. When can we get calculator expansion credit? That's a good question. So I probably won't do this till the end of the semester. After the expansion deadline, and as we get closer to that deadline I'll start announcing logistics for that, but I don't have a plan to have like an ongoing interview process for expansions. It'll probably just be doing them all in bulk right at the end of the semester, so you might have to just hang on a bit, unless I get something set up earlier. I almost certainly won't have time to do anything before break, but maybe after break, once I have break to catch up on everything, I might have logistics for you after that.